Hi, Algebra 2 Honors students. This is Stats Day 7. We're going to take a look quickly at the homework answers for Stats Day 6 on sampling distributions. So the one thing I'll say about this question is that your answers to the first part will definitely vary, right? Depending on what random integers you receive from your different trials on your calculator. You may not get the same exact, p-hats. In fact, I would be very surprised if you got the same exact p-hats that I did. But just in case you were curious about the general setup for this question, we know that we're drawing samples of size 20, so n should equal 20 in this case. The proportion of yellow in the bag is 70%, or 0.70. And remember that we don't really have to relate that to the amount of having 2,000 marbles total in the bag. We can actually really relate this by saying that the numbers 1 through 7 would represent yellow marbles, and then 8 through 10 would represent the non-yellow marbles that are in the bag. So what we need to do is we need to do a random integer. We're picking numbers from 1 to 10, and we're doing that 20 times. Stored that in list 1. I sorted it in ascending order so I can easily see what the values were in that list. And then we're looking for the numbers, specifically if we're looking for yellow, we're looking for how many of those numbers were 1 through 7. So when I did this 3 different times, I got in one trial 18 out of the 20 numbers to be from 1 to 7, then 13 out of 20 and 14 out of 20. So here were those proportions for those different samples. And I didn't find the average because it didn't say to, but the idea would be that if you average them out and you do this many times and you increase the sample size, that you're going to eventually get an average that approximates the actual proportion of yellow marbles in the bag. So would a p-hat of 0.32 be unusual? Yeah, I would say it would be very unusual, right? I mean, the actual proportion in the bag is 0.70. So therefore, it's, I guess, a possible value, but certainly would be very unusual. It's pretty far off from the actual value of p. And by the way, I'm thinking about this, 2,000 marbles in a bag. It's going to be a pretty big bag, pretty heavy too. And then would 0.8 be unreasonable? No, I actually even got a 0.9 here, right? So 0.8 is much closer to 0.7, and we can expect some sort of variability with our values for p-hat when we have a sample of just 20, okay? If we had a sample that we were drawing 100 marbles, maybe we would get something and expect something a little bit closer to 0.7. Certainly if you're drawing 1,000, we're really going to increase the chances that we get an actual value of that gets really close to the value of p in this case. All right, so if you have any questions about that, let me know. Otherwise, we're going to get into some more sampling distributions today and talking about, it gets a little bit wordy here, guys, but sampling distribution of sample proportions. So what we're going to take a look at here, see if I can fix that for you. It says below there are 3 dot plots of the proportion of tails in different simulations of a flip of a coin. So one of them represents 20 flips of a coin, the next one would represent 60, and the next one after that would represent 120. I shouldn't say it that way because it's not that the first one is 20, then 60, then 120. I actually want you to look at those samples down below, and you're going to have to determine which one goes with which. Which one was the 20 flip, the 60 flips, and the 120 flips. So it says the mean and standard deviation of the sample proportions are also shown for each of the 3 dot plots, okay? Match each dot plot with the appropriate number of flips. Clearly explain how you match the plots with the number of simulated flips. If you're unsure about this, you'll just listen in and I'll give my explanation here. But if you think you, based on yesterday's lesson on sampling distributions, can make a good guess at this, I really want you to think hard about, as we increase the number of trials, right, that simulated coin flip, what should happen to things like the mean and the standard deviation? So think about that for a moment. And if you want to give it a shot, go for it. If you're unsure, then here are the results. Dot plot 1 is representative of a sample size 120. It wound up having the smallest variability. So remember, as you increase the sample size, the variability, which is the standard deviation, is going to decrease. Okay? So that's what you're really looking for here, is that fact from yesterday that we didn't use as much, but as the number of trials increases, the variability decreases. And we should find that the mean is not changing too much in any of these. The mean is going to be really, really close to what the true value of P is, which we know for flipping a coin is 0.5. Okay, so there's my quick explanation here. I also made a note that each dot in here represents another P hat. Okay, so another sample proportion from simulating this flipping of a coin. The next one, I really was just looking at standard deviations here, guys. This one had the mid-range standard deviation. 0.064 was in between the one up here and then the one below. And then finally, the last case, this one had the largest variability, the largest spread, and you can kind of tell, just by looking at the dot plot here of sample proportions. So whichever one has the largest variability in theory should be the smallest sample size then. Okay. And notice how the mean each time, again, is really, really close to that value of 0.5. So it's not that I can use the mean to really make this determination based on sample size. The mean doesn't change. It's really the measure of spread in the data that's going to change, which is the value of the standard deviation. Okay. All right. Moving on from there. All right, on the next page, it says the same student flipped a coin 100 times and calculated the proportion of heads and repeated this process a total of 40 times. Okay. So each one of these dots below, there are 40 of them total. Each one of those is a sample proportion. Okay, so there are 40 p hats. So what we're recording here is the proportion of, in this case, we're looking at the proportion of heads. So you can see that, over here, there was a proportion of heads that maybe it was about occurred 31 or 32% of the time. Here's the case of heads occurring 50% of the time. The mean and standard deviation for the sampling distribution is 0.405 and 0.046. So based on this, do you think this is a fair coin? Why or why not? So think about that for a second. I'll show you my answer in a moment here. But remember, each one of these represents 100 flips of a coin. And we do that 40 times. So based on the mean and standard deviation, what do we think? Fair coin, yes or no? And it turns out that the answer to this is most likely not. Okay, this would not be a fair coin because 0.405 in the grand scheme of things is pretty far off from 0.50. Look how many times in those trials, those 40 different times that you flip the coin hundreds of times, that you wind up getting that true value of P to be 0.5. It really just happened once, it looks like. So with such a large sample size, would be highly unlikely that we wouldn't get something much, much, much closer to 0.50. And it seems like if we were just comparing the two decimals, 0.4 and 0.5, they seem very close to each other. But we're talking about these as proportions, they really are pretty far off. Okay, moving on from here, we can kind of make some of these same conclusions about a sampling distribution of what are called sample means. So we were just looking at sample proportions, where we're looking at the proportion of how often something happening, like getting heads or getting tails. Okay. But similar to sampling distribution of proportions, many sample statistics have the same pattern. The difference is instead of finding a p hat from each trial, we use x bar to show the sample mean. So here are some things that we can conclude which are really similar to what we've already done with sample proportions. So first one says a sampling distribution of means, which is the mean of many, many, many samples, is going to be approximately the population mean, which is a characteristic for the group that we're talking about. Okay, so the sampling distribution of means, so we're taking a whole bunch of samples, finding their average, is going to be approximately what the average is for your population. Symbolically, what does that look like? Mu of those sample means, which are the x bars, the average of those sample means is going to wind up equaling the average or the mean of the population. Okay. And then for an additional conclusion here, this is the same thing we talked about. As sample size increases, variability is going to decrease. Okay, sample size goes up, variability of the sampling distribution goes down. So as n increases, the standard deviation of those sample means, x bars, should then decrease. Same things as what we talked about for the sample proportions. Okay, so we're going to kind of walk through one example that now illustrates how this works for sample means. And that's a really quick Stats Day 7 for you. All right. All right, so what do we got going in this next example? It says example 5, several random samples of size 20 were collected and the mean SAT scores were calculated. The plot below displays the distribution of the mean SAT scores for their samples. Okay, so these are not sample proportions anymore. We're now looking at a whole bunch of different samples and the means within that sample size 20. Okay, that dot plot, you can see right below, it actually says sample means. Okay. So the first question says, is this a sampling distribution of sample means? And based on the way it's labeled, it better be, right? Yes, each dot represents the mean of a sample of size 20. Okay, so we looked at 20 students, their SAT scores, found their average, and that's what each of these dots represent. It's a group of 20 students and what the average was among that group. Okay. Part B, what is the approximate mean of the sampling distribution of sample mean SAT scores? How could you calculate that exact value? Okay, so looking at this, what we're trying to do is if we're looking at an average, you know, the average is going to be hopefully pretty close to the center of this dot plot here based on how that spread looks, right? So if we're looking, you know, it looks like it's going to be probably somewhere in between 460 and 480. There's probably a few answers that I'd accept there, but based on the largest number of dots being pretty close to 480, the approximation that I came up with is 475. If I wanted to find that value exactly, we would take the average value for all of those dots. Okay, take the average of all of the sample means that are included in the dot plot. That will give you the exact sample mean. Okay. Part C, what can you conclude about the population mean of SAT scores? What can we conclude that population mean is and why? Well, remember that the actual population mean is going to be approximate or equal to the sample mean. Okay. So it's also going to be about 475 because the mean of a sampling distribution, which is what we have up there, is going to approximate the population mean or the population characteristic there. And there's just a lot of vocabulary going on here, guys. So I know that it takes a little while to separate sampling distributions and sampling proportions and sample means, but I promise there'll be enough practice over the next few days that hopefully we'll become pretty confident with this. And I think this is the last part of the question. How would increasing the sample from 20 to 200 affect the variability and standard deviation of the distribution of sample SAT means? Well, what we've seen for the past 2 days now is anytime we increase that value of n, we're definitely going to decrease that variability, which is in turn going to affect the standard deviation and decrease it. So since n increases, the variability decreases, so the standard deviation of the sample SAT means should also decrease. And that's pretty much it. And I know this feels really just so different than a lot of things we've done this year because it's a lot of just explaining things and writing little short sentences here and there. But I hope that the concepts are making sense to you. And certainly when you go to try that homework 7 here, if you have any questions at all, you will let me know. All right. Okay, we'll touch base soon. That's it for today.